I'm setting up an activity that we can do at home to investigate simple harmonic motion. We're especially focusing on period, amplitude, and frequency. I've got a simple spring here that could be ordered online, pretty inexpensive to come by. I also have some PVC that I've used to suspend the spring. You certainly don't have to use PVC. You could hang it from anything that's available to you. But I had a lot of this PVC laying around the house, so figured I'd use that. I also started to create a measurement device here that I can use for the activity. And I'm just gonna try to measure off every 10 centimeters. I'm putting a mark on this PVC. And it's just gonna be a good guide for me. I wanna be able to know how far I'm pulling down the spring. And so this should help me to gauge that. So I've got several springs of the same type here. There's a long, a medium, and a short. They're all clearly the same style, same material. Some other materials you'd need would be just scissors, string, and perhaps some tape to mark the measurement device, unless you have a meter stick available. So yeah, if all you have is a ruler, that could potentially work, but it kind of depends on how far you're going to displace your spring. That's why I went with the PVC pipe here. That'll make it easy to measure something on this scale. Okay, so we want to hang something from our springs. I had a weight set that I was able to pull some masses from. If you don't have that, you could use a bunch of quarters potentially. These are objects where we could look up the mass of what they're supposed to be. Washers from a hardware store could be something that you could use. If you have access to them, then hooked lab masses could be good. All right, so let's take a look at the description for this activity. It says we're going to investigate simple harmonic motion on a relatively large and relatively slow scale. This activity is designed to introduce concepts of waves, and sound waves have frequencies that are quite high compared to the frequency that we're going to see in this situation. So we want two setups. You don't have to do them at the same time. So in this activity, we're going to investigate the formula for frequency. And it would be ideal to do two different setups which have different frequencies. It doesn't really matter the exact weights that you use or the exact spring that you use, but mainly we're just trying to see that there's a difference between the two setups. So perhaps what I'll do is I'll use the medium spring with a 2.5 pound weight. And then for my second setup, I'll use the short spring and two 2.5 weights together. So that'll give me two very distinct systems to look at. And like I said, it doesn't matter too much the exact mass that you use here. I'm going to go with the metric system, 1.1 kilograms. I'll write that down as the mass that I'm using for setup 1. And for setup 2, I'm going to use 2 of these. So that's going to make 1.1 times 2, which is going to be 2.2 kilograms. The next thing I need to do is find the equilibrium length of the different springs. So the equilibrium length, it's going to be the length after it's been stretched by the hanging mass. So I'm going to attach the medium length spring now to a loop of string that I have on my PVC. Okay, so that's ready to go. I've got a 1.1 kilogram mass with a loop on it as well. And let's go ahead and hang that from the spring. Okay, at this time we can see that the system has reached an equilibrium. The forces on this hanging weight must be balanced. It's being pulled down by gravity just as hard as it is being pulled up by the spring. And this is going to be what's called the equilibrium length at this time. So if we want to measure that length as best we can, I'll use my measuring device here. And each one of these markings is 10 centimeters. So the length of it I determine is 10, 20, 30, 40, 50, 60, 70. It's between 70 and 80. So I'll go with 73 centimeters. So let's write that down. And I could add uncertainties to this if I want to. I could add it later if I wish. Okay, so now we need to hook up the second system. All right, so for the second system, I said that I might use 2 of these 1.1 kilogram masses. However, I've already got one in use. So instead, we'll use this one. This is the next bigger size. This is 5 pounds or approximately 2.3 kilograms, twice as massive as the one that's hanging here. I'll attach that to the short spring. Okay, there we go. So now let's measure the length of the shorter spring. It's 10, 20, 30, 40, 50, 60, 65. And the mass claims to be 2.3 kilograms. Okay, so those are our 2 systems. What we're going to do next is we're going to create a displacement of the mass by pulling it down by an arbitrary amount called x. Yeah, so for spring 1, it looks like, let's see, that's 10 centimeters, 20, 30, 40 centimeters, and the bottom of our spring is at about 48 centimeters initially. I'm going to pull it down by 10 centimeters. So I'm pulling it down to about 38 centimeters at this time. So right now I'm storing potential energy in the spring, and that potential energy can be used once I let go in order to put the mass into motion. So let's let go now. And we watch it oscillate up and down. Our goal in this activity is going to be to measure the time between oscillations. So every time the mass goes down to this point and then goes up and then back down to that same point, that's a full oscillation. Okay, so from here up and then back down, that's one oscillation. If we let it go for 2 oscillations, that would look like this. Okay, so here it went up, and then down again. That's 2 oscillations. 3 oscillations would be to let it go up and down, up and down, up and down again. So that was 3 oscillations. What we want to do is time how long it takes to do 1 oscillation, and then how long it takes to do 2 oscillations, and how long does it take to do 3 oscillations. And we'll just keep going like that, and we're going to create a graph of cycles versus time. So I'm going to use my phone stopwatch to keep track of how long the oscillations take. So I'm going to pull the spring down by 10 centimeters. When I release the mass, I'm going to hit start on the stopwatch. The mass is going to go up and then come back down, and when it comes back down to the point where I had released it, I'm going to hit stop on the stopwatch to see how long a single cycle takes. Okay, ready, set, start, stop. It was 1.03 seconds. So let's write that trial down. Okay, so our displacement was 10 centimeters. For 1 oscillation, it required 1.03 seconds. The next trial will be for 2 oscillations. So I'm going to reset the timer, and I'm going to pull the mass down by 10 centimeters, and I'll hit start when I release the mass. It's going to go up and then down and then up and then down, and I'm going to hit stop at that point. Okay, ready, start, stop. 2.26 seconds. Next we'll do 3 oscillations. So I'll reset the timer, pull it down, and we'll hit start. 1, 2, 3. I get 3.43 that time. Start 1, 2, 3, 4. And start 1, 2, 3, 4. Start 1, 2, 3, 4, 5. Start 1, 2, 3, 4, 5, 6. Start 1, 2, 3, 4, 5, 6. Start 1, 2, 3, 4, 5, 6, 7. Start 1, 2, 3, 4, 5, 6, 7, 8. Start 1, 2, 3, 4, 5, 6, 7, 8, 9. Start 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Start 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, I've got the times for 1 through 10 oscillations for setup 1. I now want to try the same procedure for setup 2. And we'll see if there's any difference in these results. Okay, now the time that it took to complete 1 full oscillation is known as the period of the oscillator. It also has the letter big T. Now let's see what the period of setup 2 is. And keep in mind that's in seconds. The period is in seconds. So let's try it now on setup 2. And we'll see what its period is. And right now the spring is located at 10, 20, 30, 40, 55 or so, 55 centimeters above ground. So I'm going to want to pull it down to about 45. So that's going to be a 10 centimeter displacement, just like I did for the other mass. Trying to keep that consistent here. Okay. So let's get our timer, and we'll time how long it takes to do 1 oscillation, which is the period of the oscillator. Okay, so I'm going to hit start, and stop. So it was about 1.31. And so the time that it took for this setup was longer than the time for the other setup. So it has a longer period, which means it's oscillating a little bit more slowly. Now let's try it for 2 oscillations. So let's see how long 2 oscillations takes. Start. 1, 2. 2.59. One, two, three, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. And finally, 10 oscillations. Start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so we found here that the time that it takes for an oscillation in setup 2 was a little bit longer than the time it took for setup 1 to complete a full oscillation. It wasn't a big difference between the two, but there was a difference. So what we'd like to do now is plot these as graphs where we're going to have the time on the horizontal axis, and I'm going to put the oscillations actually on the vertical axis. Keep in mind that this is opposite of how we normally arrange a table of horizontal and vertical. Usually we put the horizontal on the left and the vertical on the right. So we do want to switch that when we go over to a graphing program. Okay, so I'm going to go to desmos.com. I'm going to click plus in the upper left to add a table. And then I want to put my times on the horizontal and my oscillations on the vertical. So that means that the 1, 2, 3, and so on needs to go in the Y column, and my times will go in the X column. The type of graph we're trying to create is cycles versus time, so that's why the time needs to be on the horizontal X axis. All right, let's see the data that we've entered. And we get an almost perfectly straight line scatter plot. Going to want to do regression in order to get the best fit line that goes through those points. And so the command in Desmos for doing linear regression is going to be y1 tilde mx1 plus b. Interestingly, I got a R value of 1, which means that the data is just about perfectly linear. I only did 1 trial for each number of oscillations, so I'm a little surprised that it's claiming to have perfect correlation. But now the M value is the slope. of the line. And the slope has meaning in this situation. The slope is going to be what is known as the frequency of the oscillation. It's the number of cycles per second that are being completed. And so this is a M value of 0.843 or 0.84. And so let's just write that the slope for setup 1 was 0.84. And this is going to be cycles per second. And that is because we have cycles on our vertical axis and seconds on our horizontal axis. So the slope is going to be the rise over the run. So that's going to be cycles per second. Let's now plot our other data set. I can go to a new field and click plus and add a new table. And let's just enter this set for setup 2. Okay, so the orange is setup 2. Let's do the regression now for this plot. I'm going to type in y2 tilde mx2 plus b. So this is data set 2 in Desmos. Every data set has a little subscript after the x and y. So I did y1 tilde m x1 plus b for set 1. And now I have to type in y2 tilde mx2 plus b for set 2. And that references these columns. And as we can see here, the slope is just a little bit less steep than it was for setup 1. And we have, again, a very high correlation, 0.9999, almost 1, which means that a linear model is a great model for this data. And we have a little bit lower slope than before. Before I had 0.84, now I've got 0.78. And so what that corresponds to, in a physics sense, is that the frequency of setup 2 is lower than the frequency of setup 1. In other words, it takes longer to complete oscillations for setup 2 than it does for setup 1. This results in less cycles being completed per second overall for setup 2. Okay, now the regression takes into account all the data points that I had entered. And so I'm going to get my best estimate of the period now for each setup. Now, period has a formula of t equals 1 over f, where the t is the period, it's called, in seconds. And f is going to be the frequency in cycles per second. So what I'm going to do for setup 1 is do 1 over 0.84 to get the period. So I actually get 1.19, and that's seconds. I noticed that does differ a little bit from my very first reading. It's not uncommon for that first reading to be a little off. It's the shortest time span of all of them. So the chance of making a significant human error there is pretty high. And now let's do it for setup 2. I get 1.28 seconds. So a little bit longer period, not surprisingly, for the slower mass. On my first trial for that one, I did get it pretty close to that. I had 1.31. Now, a trial where there's expected to be less percent error would be when you have a lot of oscillations, like 10 oscillations. So what would the period be? Yeah, so just for that last trial, we could find the period by taking the total time and dividing by the number of cycles that were completed. So in this case, like for that last trial there, the average period would then be 11.72 seconds divided by 10. So that gives us 1.17 seconds per cycle. So that's going to be a little bit more reliable result. As we can see, I definitely underestimated the period. I might have had a little bit slow reaction time at one point, or maybe I arbitrarily stopped it a little early. But this is a lot closer to the true period, I'm sure. Similarly, if we do that same thing here for setup 2, we do 12.79 seconds divided by 10 cycles, so that would be 1.28 seconds per cycle, and that matches up really well with the regression.